Hi guys, Ms. Shearhart here, and today we're going to be talking about intermolecular forces. These are the forces between molecules, not within the molecule. Within the molecule, those are the bonds. So between molecules, we can see what type of forces we have by first testing, are there any polar bonds? This is where we take the electronegativity into consideration, our delta En value. So if we look at water, H2O, okay, if we were to draw water, simply, we would draw it like so in 2 dimensions, and we would take the electronegativity difference between the oxygen and hydrogen, and we find that it lands us between this 0.5 and 1.7 difference, which are our polar covalent bonds. If it was between 0 and 0.5, it would be a non-polar covalent bond. And if it was greater than 1.7, it would be an ionic bond. So if we get electronegativity difference in this range, we're dealing with polar covalent bonds. So now we have to figure out, do those polar bonds cancel each other out? And for that, we need to look at the geometry. So first we have to draw water in 3 dimensions. Using our VSEPR table, we can see that water is a bent or angular shape. So it actually looks like this. So if we draw a few water molecules, there's billions in a glass, but if we have a few water molecules like so, we're looking at the forces between the molecules themselves. So there's an attractive force between one oxygen of one water molecule to the hydrogen of another water molecule. And that's because this is a bent shape where these polar bonds do not cancel out. So I have a polar bond here and a polar bond here. So if I add my polar bonds tip to tail, it's like adding displacements in physics, and I end up with an overall dipole like so. Same with this in this molecule and in this molecule. So now this slightly negative oxygen, this slightly positive hydrogens, I have an attraction between the slightly negative and the slight positive. So I have dispersion forces, dipole-dipole attractions, and hydrogen bonding. Dispersion forces are an intermolecular force that exists in all molecules. They are our weakest kind of intermolecular force. Dipole-dipole only exists between polar molecules. So when I have water, because it has polar bonds that do not cancel each other out, it is a polar molecule because it has an overall dipole. Therefore, it has dipole-dipole forces between molecules. My last and strongest force is called hydrogen bonding. This is just a special case of dipole-dipole. This only occurs when we have OH, NH, or FH bonds. So because the electronegativity difference is so great between those atoms, we have such a great force that happens when we have those between one molecule and another. So we can draw 3 dashed lines between one water molecule and another, signifying that there are 3 forces between the water molecules, which means they are greatly attracted to each other. If we want to heat water up, we will be breaking these intermolecular forces when we heat it. That's why water has such a high melting and boiling point. A boiling point of 100 degrees Celsius is very, very high because there are 3 forces to break with heat. And when we break all 3, we allow each water molecule to be free from the rest, and then it is free to be a gas and float away from the others. If we look at other organic molecules, first we must be able to draw them in 3 dimensions. The good thing is that they all contain carbon, and we know that carbon is tetrahedral around its bonds. So if we are to draw something like methanol, CH3, OH, I'm drawing a tetrahedral structure around the carbon, followed by a bent structure around the oxygen for my OH bond. So here I have electronegativity difference that are less than 0.5, they're 0.4, so these are non-polar bonds. This is a polar bond with a more electronegative oxygen, and this is a polar bond as well. These do not cancel each other out, therefore I have an overall dipole, and this is a polar molecule. The fact that methanol is a polar molecule makes it dissolve in polar water and also gives it a higher melting and boiling point than a non-polar covalent molecule. Something like acetic acid CH3COOH, we just draw one at a time. So we have our tetrahedral structure around our carbon, C, double bond O, and our trigonal planar around this carbon, and our bent around the oxygen. So we essentially have to go from one shape to another, tetrahedral, trigonal planar, and bent. This allows us to see that this again is a polar molecule because I have non-polar bonds here, so this is my non-polar section. But here I have a polar region, polar, polar, and these do not cancel each other out. Therefore, this is also a polar molecule. So analyzing whether or not an organic molecule is polar or not helps us decide whether or not it will have a high melting and boiling point, and also what its solubility is. The greater the non-polar region that I have, the less soluble it will be. But the longer and larger the compound, the higher the dispersion forces, giving it a higher melting and boiling point.